Welcome to the next lecture of half-life, propagation and termination step of radical chain polymerization. So, if you recall that previously we studied about the concept of precipitation of polymer. Then we discussed about the polymer and different type of approaches attributed to the process analysis of polymerization process. And then we discussed about the initiation part. Then we discussed briefly about the redox initiation, especially we gave major emphasis to the redox initiation. Now, in this particular chapter, we are going to discuss about the stability and half-life of initiator. Now, this is a very important concept of initiator because you cannot overlook the importance of initiator in any kind of polymerization reaction. So, the stability and half-life time of the initiator is very important. We will discuss about the dependency of polymerization rate on initiator. Again, this is the mathematical approach. Then we will discuss about the dependency of those initiator on monomer, that is initiation in either aqueous media. So, let us start with the stability and half-life of initiator. Since we discussed about the decomposition concept of initiator, and this particular decomposition concept is very much important in while discussing this stability and half-life period of initiator. Now, the rate of decomposition of initiator usually they are different due to their individual chemical structure. If you recall, in the previous lecture we discussed about various initiators, and in situ we gave you information about the structure of those initiator. So, the radical produced during say homolytic cleavage also pose the different dissociation behavior, and if you recall that we discussed about the rate of dissociation of those initiator also. So, when we talk about the rate of dissociation or dissociation rate constant Kd. This Kd is greater for acyl peroxide than alkyl peroxide. Now, because the radical RCOO is more stable than the radical RO, and for Rn and R, this Kd is increases in the order. And this was very much particular analysis is very much being carried out by Audion and Koning. Now, here R stands for alkyl, benzyl and tertiary. So, if you see the increasing order, you can find it out this place. Now, the differences in the rate of decomposition of various initiators, this can be expressed conveniently in terms of initiator half-life, and sometimes referred as T half, which is in a broad spectrum defined as the time required for a quantity of initiator I to reduce to half of its initial value. So, this is the half-life time attributed to the time factor. Now, if in this particular table you see that people already studied about the dependency of half-life or half-life approach of different initiator with respect to the temperature profile. So, this is a very useful information carried out by the George Audion. Now, in this particular approach, if you see that we have enlisted different initiators like AIBN, benzoyl peroxide, acetyl peroxide, tertiary butyl paracetate, cumyl peroxide, tertiary butyl peroxide, etc. Then if you see that here we have enlisted the different temperature profiles. So, you can find out the ways based on your requirement that how much the half-life that particular initiator possesses. So, this is a very useful information attributed to this particular concept. Now, before we discuss further, then we can have a look about the mathematical approach of these half-life of initiators. So, initiators, that is rate of disappearance of initiator I. This with respect to time, this can be given as minus d I over dt, which is equal to kd I. So, where concentration of initiator is given by I, that is the concentration of I at time t. Now, if we integrate both the sides with the limits sides, now at t is equal to 0, the initiator concentration may be put as I naught. Now, at t is equal to t, that the concentration I may be represented as I. So, if we perform the integration, then this I naught, this can be represented as 0 to t minus kd dt, or minus kd t is equal to ln I upon I naught. So, this is the thing. Then we can go with the I is equal to I naught to the power e to the power minus k dt, or ln I naught upon I is equal to k dt, or t is equal to 1 upon k d ln I upon I naught upon concentration of I at time t. Now, let this is one equation. Now, let us say that when I is equal to I naught on 2, that is the half of the initial concentration, half of the initial concentration, then t is equal to say t by 2. So, for t half is equal to 1 upon k d ln I naught upon I naught by 2. So, t half is equal to 1 upon k d ln 2, or t half is equal to 0.693 upon k d. So, this is the half life equation, which is again a very useful equation for pertaining this type of information. Now, the half life of initiator provides information regarding the stability of that particular compound. Now, higher the stability, greater the half life of the initiator, and thereby the higher the dissociation constant. So, it gives you an opportunity, or it gives you an information related to the usefulness of that particular initiator in a particular polymerization reaction. Now, let us have a look about the dependence of a polymerization rate on initiator. Now, we have previously derived the rate of propagation in the previous lectures, which can be represented as Rp is equal to Kp Fkd Kp square upon Kt to the power half, concentration of a monomer, concentration of initiator to the power half. Now, it shows that the rate of polymerization depends on square root of concentration of initiator. Now, several monomer initiator concentration or a combination people have tested and confirmed that the square root dependency at lower initiator concentration are valid, and the foremost work being carried out by George Odion. Now here you can see, or you can have a look about the square root dependency of initiator with the help of this particular plot, where you can see the dependency of the polymerization rate with respect to the concentration or initiator concentration, and you see that the straight line is coming out. So this type of approach or this type of a plot helps you to find out the proper efficacy of initiator. Now, in some other circumstances, variation from this behavior is usually observed. At a very high concentration of initiator, the order of Rp or rate constant for propagation, that is dependency on concentration, initiator concentration can be found to be less than half. Now, sometimes people ask about the reason for this particular thing. The reason behind such divergence, this can be attributed to the decrease in the cage efficiency of F. So, if you recall that we discussed the concept of cage efficiency in the previous lectures. Sometimes this may be due to the fact that the concentration of initiator radical, it increases, and thereby the probability of facing of a propagation of radical with initiator radical also increases. Therefore, the chance of termination increases. So, all these things, if you see that they are interlinked, and this phenomena can be decreased in the case in the concept of a case efficiency. So, people have discussed that at what point of time it decreases. So, Berger et al. They find out that it decreases with the cage efficiency F. So, this relates the dependency of polymerization rate on initiation. Another reason for this divergence, this can be attributed with the fact that with increase in polymerization reaction, the monomer concentration usually decreases, and that's quite obvious. So, when the monomer concentration becomes too low, that the initiator radical starts neutralizing the propagating radicals, because they are present in the sufficient quantity in that reaction mass, and they are not finding the monomer concentration at par with their requirement. Therefore, they start neutralizing the propagating radicals, and sometimes this phenomena is again very useful to truncate the polymerization step at any point of time. So, this can also be happened if a bimolecularly decomposing initiator generate one radical having very less or sometimes even without having any tendency for chain initiation reaction, but sometimes they may have the potential to terminate the propagating radical. So, this is again a very important phenomena which we need to address. Now, as the initiation reaction proceeds, the concentration of unreacted radical increases with the time, and finally, when entropy decreases, this is if you see that this is the one of the most important phenomena to carry out the efficacy of any reaction. So, when the entropy decreases, it starts reacting with the propagating radicals. So, this can happen if one of the initiator radical, they have the bond dissociation energy sometimes lesser than the energy required to break the bond of monomer. Now, when the propagating radical forms, the energy of such radical is enough to form a bond with the propagating radical. So, sometimes this can reduce the dependency with the concentration of initiator to 1/3 of the concentration. This people have already reported in the literature. Now, these three type of termination behavior which we discussed in the previous slides, this can be termed as a primary termination, because the termination occur due to the primary initiator radicals. Now, if the radical passes on its character to other reaction mass, then it may become the secondary one. Now, let us have a look about the primary termination aspect. Now, here we will discuss this particular important approach, termination. Now, here this Mn is the propagating radical. This acts with the initiator radical. This is the initiator radical. This is my rate constant. It forms this one. Now, here this one is represented as KTP. Now, this KTP is the rate constant for termination due to primary radicals. Therefore, when primary termination absolutely proceeds, the whole termination step, then the rate of propagation can be determined as Rp is equal to Kp Ki, concentration of monomer, so this is the thing which gives you the rate constant or rate of propagating reaction. The rate of a reaction is directly proportional to the square root of monomer concentration, as it is evident from this particular equation which we developed previously. And the rate of a reaction is independent of initiator concentration, but usually depends on Ki. So, in some cases the dependency of Rp, that is the rate of propagation, can be greater than half for the initiator concentration. So, this dangerous reaction, I mean, this is a very undesired situation. So, this dangerous reaction can happen if the radical do not terminate, or sometimes it may happen that the termination slows down. So, if they do not terminate due to localized increase in the viscosity of the polymerizing system. So, this is a highly undesirable situation. Sometimes usually the rate of a polymerization shows first order dependency on monomer concentration. Let us give an example of methyl methacrylate polymerization. This shows the first order relationship, and hence the polymerization rate can show higher than first order dependency. The best example of this type of polymerization of styrene in chlorobenzene solution at 120 degrees Celsius. This shows the 1.5 order of dependency, and the monomer was initiated tertiary butyl per esters. Now, if styrene is polymerized in toluene solution at say 80 degrees Celsius using benzoyl peroxide initiator, then the order of dependency increases with increase in the monomer concentration, and people have reported that it is 1.18 at when the monomer concentration equals to 1.8 and 1.36 at when the monomer concentration equals to 0.4. So, Hermann, they have carried out this particular study way back in 1953. So, people debated about this particular character. So, one explanation for such change, this can be attributed to the fact that the rate of initiation, unlike the assumption whatever we have taken, that depends on the concentration of monomer. Now, if initiator efficiency is directly proportional to the first order of monomer concentration, then Ri depends on the first order of monomer concentration, and rate of propagation dependency will increase from half to say 1.5. So, the mode of initiation such as thermal, sometimes photolytic, sometimes redox or sometimes ionization reaction, they also affect the monomer behavior. And once the behavior of monomer changes, then the polymerization rate subsequently being changed. Some of the compounds or the functional group when present or sometimes attached with other compound in an initiation process, they can also improvise the dependency of initiation reaction with respect to the monomer. So, people have carried out extensive work in this particular approach. One example is the tertiary butyl hydroperoxide styrene system. So, when used as an initiator, the presence of styrene increases as the initiator efficiency for the monomer concentration and from the order of 1 to 1.5, because in situ presence of styrene within the system. So, when tertiary butyl hydroperoxide or styrene when used alone, they show the dependency of the order of 1. Now, this increased decomposition rate is sometimes said to be favored by the molecule induced homolysis reaction, and it is represented as monomer, initiator, and like this. Now, this type of initiation phenomena is somewhere found in the redox initiation. Now, let us move to the redox initiation. Previously in the previous lecture we studied brief about this redox initiation. Now, we can say that virtually all radical chain polymerization reactions, they require a unique and independent initiation step in which free radicals are sometimes being generated in reaction mass. Now, the initiation step usually it is very critical, and activation energy, it is a very common phenomena. So, the activation energy barrier, this plays a very vital role during the selection of initiator compound, as well as what kind of initiation process being used for a specific polymerization reaction. So, we have discussed a priori that the bond dissociation limit for covalent bond breakage is somewhere around 100 to 170 kilojoule per mole through thermal initiation reaction. They are very narrow, hence it limits the use of compound to those who are having activation energy either above or below this limit. Now, second important thing which we need to address, that the concentration of free radical present in the process, which is increased to a substantial amount, that can lead to unwanted reactions or reaction such as primary termination or sometimes self combination. So, this type of termination sometimes may lead to the improper product concentration, improper product parameters, and you may face the difficulty during the course of further processing. Redox reaction, sometimes people say that this is another kind of initiation phenomena where electron transfer sometimes carried out between the two molecules through either oxidation, reduction reaction or some other way. Now, then the bond dissociation occurs at the acceptor molecule to generate a free radical. Now, this particular thing is again important because people may ask that what should be the priority order to generate the free radicals. So, this solves this particular query. Now, redox initiation or redox activation, they found several application in the polymerization industry. So, it is always favored for conducting low temperature emulsion polymerization. So, this is very important thing which one should have in their mind while designing the polymerization process for various industries for a very specific use. Now, redox initiator, they have advantage of lower activation energy for initiation reaction, and they can produce the radical to a substantial amount over a wide range of a temperature. Now, because of this lower activation energy, this is somewhere in the range of say 40 to 80 kilojoule per mole. This demands redox initiation, which can be conducted various chemical reaction at a very moderate temperature range, sometimes below 50 degrees Celsius or sometimes even lower than 0 degree Celsius. So, this is again a very important aspect to look into. The lower activation energy greatly reduces the possibility of side chain reaction and increases the yield. So, this is the plus point of these redox reaction, and these reactions have a very short induction period. Therefore, the reaction proceeds quickly. So, the economics of the polymerization process can be improvised. However, these reactions also have some limitations such as lower efficiency than the thermal initiation, and you need to put forward a complex control of those initiator. So, these are some of the limitation of these redox initiation. Now, secondly, the addition of charged metal ions and sometimes the counter ion, they can affect the electrostatic stability of the system. So, these reactions are also referred as the pH sensitive reaction. Therefore, usually the weak acids, they are used to perform certain chemical reaction. So, these are the either you can say the plus point or the negative points, etc. Now, in this particular chapter, we discussed about the concept of redox reaction. We discussed the concept of a half life, and we had a discussion that how this half life played a vital role in deciding the fate of the polymerization reaction. We developed the mathematical equation which pertains to this half life concept, and we had a discussion about the various half life attributed to the different type of initiators and what is the dependency over the period of time. We had a brief discussion about the bond association and its energy and in situ effect to the initiator. So, we will carry out this particular discussion especially related to the initiation in the aqueous media in the next lecture. Thank you very much.